Okay, now we're getting to the big leagues. Acid-base titrations. So we've done these before. We did these with strong acid, strong bases. Endpoint was at 7. Equimolar, all the good. Might want to reflect back in thinking about pH and how much concentration and volumes of things that we've used, but those are essentially the same. However, we're introducing when you have something like a weak acid and a strong base. So in the case of this, acetic acid, strong base, your endpoint is going to be above 7. And that's because even though all your hydroxide is left over, you have a conjugate base now with water. So therefore, that's where our endpoint is going to be higher than pH 7. However, you still see equimolar amounts. Again, if you have a strong acid and a weak base, it's going to be below 7 because the idea you have more acid in concentration, and so therefore it's going to be below. Again, simple things to understand and have when you just are looking at a a titration curve. However, keep in mind that if you have a strong acid and strong base titration, it might be the other way. So the idea is that you don't always titrate acid with a base. You might do a base with an acid. It'll look different, but same ideas, right? pH is still 7 at the end point. Keep in mind of that. This is what I've seen quite a bit in my time as a teacher. Addition stuff, kids understand. Subtraction stuff, less kids understand. Multiplication, kids understand. Division, less kids understand. Acid added to a base, kids understand. Base added to an acid, less kids understand. Those kind of situations that you need to be comfortable seeing it both ways. Ka calculations, understand. Kb calculations, less understand. That's where I've seen so many things available in chemistry that just want to be comfortable seeing it many different ways. More concerning the titration curves for the 3 videos on APC, I highly recommend those because they're really well laid out in the vids. So I think those are very good. I'm going to go through some examples and stuff, but again, if you're looking for others, those look pretty strong. So titration calculations, there's really 5 different types. These are also covered in Pearson, I think, quite well in print. So I would suggest, again, another good resource for those. Now, you might be asking, oh my God, this looks like the worst FRQ ever. You're not going to probably do all of these in one. You might do this one in one. You might do this one in one. You might do, starting pH. That could be a simple multiple choice question. But you're going to have all parts of these going on. So, starting pH, where you're starting from. Early on the titration, this is where you have it as a buffer. So you need to do some stoichiometry and then the Henderson-Hasselbalch. Equivalence point, that's where they're in the middle. You don't have a buffer anymore. All you have is the reverse reaction because of what you're starting with is what you're ending with. Maybe calculating a new K value, ice table, then pH. So a lot simpler steps. Halfway point, that's halfway to the equivalence point. This is a fun little factor that the pH equals the pKa. Why? It just does. And then towards the end of the concentration, you have extra titrant left over. You added too much, stoic, and then a simple pH. Okay, so we're going to walk you through each of these, not in the 1 through 5 order, so keep that in mind. So what this looks like here on a titration curve, 5 is endpoint, 3 equivalence point, 2 somewhere in the buffer range, so early on before it gets too close to the equivalence point, the halfway point, and where you start. So we'll start off these. You can see that there's these little numbers. Those refer to the steps, step 1, 2, 3, 4, 5. So we got a weak acid with base. I'm going to start off with my amount of weak acid. Got our Ka given. Calculate the pH before any titrant is given. So we just have our normal concentrations in. This is where we go back to the x squared over the original concentration is equal to Ka. That gives us our x. X is our hydronium concentration. Negative log of that, our pH starting point is 2.78. So this is kind of old hat, not too new. So, seems easy? That's the end of the easy. Okay, so this is the second part, where we're past the starting point, we are now in buffers, and we're not yet at anywhere of the halfway point. So 10 milliliters of the strong base is added. So we're no longer as acidic, we've included some base, we're increasing in pH. We need to first determine stoichiometry. We will have a conjugate base, and then we will use the Hee-Haw equation, okay, Henderson-Hasselbalch. So the first thing we need to do is determine how many initial moles of our acid did we start with, and how many moles of base have been added. These are mole tables, not ice tables, essentially because we have no X going on. You can see they use millimoles. Millimoles would be 10 to the negative third. That always confuses me so much, but I wanted to show it to you in case you're comfortable with it, because then you're just dealing with regular integers and decimals and stuff. So 3.75 times 10 to the negative third, stoichiometrically added to 1 times 10 to the negative third, right, will get us 1 mole of water and 1 millimole, or 1 millimole and 1 millimole of the conjugate base. Likewise, taking away 1 millimole of my acetic acid. So, remember when I talked about adding volumes? This is where you need to be careful. We're using these in moles because our volumes have changed now that we've added. So, when we're thinking of what is the concentration of the remaining acetic acid, we have the number of moles that are still there divided by the additive volumes of the original volume of the acid plus the volume of the base. The conjugate base now, we have its small amount of moles with the same volume. So we have the acid and its conjugate base in its concentrations. So we can use the Hee-Haw to where the pH is the pKa, which we already are given, plus the log of the base over the acid. Make sure you put it in correctly. pH is 4.31, expected to go up from the original, not quite at 7 or anything even close. Now let's say we're doing the same thing, but a different volume, 25 milliliters. We have the same idea, stoichiometry, buffer, we have the conjugate base, acid. So original amount of the acid, the amount of the base, again using millimoles, can be one way of going about it. And we can see that we now have different amounts of our conjugate base and less of our original weak acid. Again, the moles divided by the total volume. Moles divided by the total volume. We have our amounts here. Again, plugging it into our Henderson-Hasselbalch, Hee-Haw, we have our base over our acid, 5.05. Makes sense, we added more base, therefore our pH should rise. So if you thought that was enjoyable, guess what? It gets worse. So, equivalence point. We've added an equal amount, okay? So where we have the moles equal the moles of base equal the moles acid. Again, same concentration, same amounts. And now we have water and the conjugate base. So we're at the equivalence point. We know we're adding base to acid, so our equivalence point should be higher than 7, more basic. So when we're looking at these, we have to reverse the reaction and make an ice table. So far, we haven't been doing ice tables. Okay, this is when we actually put it on ice. So we need to determine what is the concentration of this conjugate base. We have the moles divided by our total volume, our beginning, and how much was added as a base. to get 0.06 molar. So this is going to be reacting with water to make, again, the conjugate acid and hydroxide. We can forget what X is because we have 1 times 10 to the negative fifth. I think it's 1.8 times 10 to the negative fifth. So this is going to be super duper small. Remember, in order to get our KB, it's 1 times 10 to the negative 14th minus what we've already been provided. This is where our KB is super small. That's why you can see we can drop the X entirely because this is way tiny. So our KB value equal to our conjugate base times X. We now can get the hydroxide concentration, and from the hydroxide concentration, do the pH calculation. Remember, this is hydroxide. This is one way to go about it, to determine the pOH and then to determine the pH. So again, think about, does this make sense? You got a weak acid, strong base, equivalence point should be basic. So yeah, it does. It makes quite a bit of sense. It's a lot to get through, but again, doing some practice and getting some of these down is really going to be helpful for you being able to do any parts of these along the road. So you might be thinking to yourself, geez, can this get any more hard? The answer is no. It actually gets simpler now. So at 4 is the halfway point. So if you know it took so much base to get to the equivalence point, the halfway point is, guess what? Halfway. And being halfway, the pH is equal to the pKa. So you plug it in, 4.74. So again, why even calculate it? It's a nice point to have, right? Because really you have your starting point and your equivalence point, which is way high up. So halfway should be halfway upon the curve as it increases before it sharply increases to your equivalence point. Also, when doing a titration, you can figure out what Ka is by finding the pH at the halfway point. And guess what? I believe that's what we're going to be doing in our lab. So now we've gotten to the last part, the endpoint. Have a whole bunch of base added up. No buffer. All the weak acid's gone, but we're still way past the equivalence point. So really what you need to determine is how much excess hydroxide did you have? So you've had so much base. We had our acid. We made that the limiting reactant. That's why there's none left. But we have this as an excess reactant, our 1.25 moles. So from there, we have our moles over our total volume. Again, watch that total volume to get you your hydroxide, pOH, pH 12.22. Makes a lot of sense because it's pretty high up there. All right, so some final things to wrap up this section. Selection of indicators. So if we had an equivalence point of a strong acid and base, we can see the transition of methyl red and thymol blue would be poor choices in either of these cases because we wouldn't really be able to tell you where the equivalence point is. It would be kind of off the scale. It'd be yellow all the way throughout. If we wanted to have one that's a strong base with an acid, and I knew that because it's above 7, thymol blue would be a great indicator of choice because that's where it's going to transition from its blue to yellow form, and you'd be able to identify the equivalence point based on the indicators alone. So how do you know which indicator to pick for a reaction? You want to pick one that has the pH range that's plus or minus 1 from the pKa that you're doing. So if you have a pKa of 2, you want to choose something from the 1 to 3 range, something like thymol blue. So keep that in mind that as you're going through these, really they're just trying to have, do you have this connection between pH and pKa that can you choose the right one based upon where it's going to transition? And again, the transitional colors will be in between these. So for example, like looking at phenol red from yellow to red, that looks like it's going to probably happen in the 7.4 range, So that's where you're going to want to have it go from yellow to red. So keep in mind as you're looking at these of which ones you want to choose. There's some other acid-base indicators. Again, you're not going to be memorizing these. They're not keen on going, oh, you need to know methyl orange is this compared to alizarin yellow and what these colors are. But you'll be given this information and you need to interpret where should I be using these and with what. Now, polyprotic acids. Whoa, wasn't one acid enough? You don't need to compute these, okay? But you do need to identify major species along the way. So, for example, when we're thinking at this triprotic acid, at the midpoint, you have these being equal, okay? All these being equal. But once you go past it, this has the more conjugate base. So there's more PO4 3 minus, should say 3 minus up there, than there is the HPO4 2 minus. Here there's more HPO4 2 minus than H2PO4 minus. Again, more phosphoric acid present than its conjugate base. At each of these midpoints, they're equal. Okay, each of these midpoints, they're equal. But again, thinking about what more do we have in prominence here, well, that would be the HA2 minus past the midpoint. So from midpoint 2 to 3, you've got the second conjugate base and so on. So keep that in mind. You'll get to do some of these in an activity I give you. And again, these would be more multiple choice type questions rather than so much for a FRQ type. All right, it's been a long one, but come on in with your questions. I'll be sure to help. Take care. Bye-bye.